All right, let's get started. So, yeah, I'll post the solution of the midterm either today or tomorrow. So you can see probably it should be very easy, right? Yeah, who believe it's extremely easy? Good, good.
I don't know if I would say extremely, but it was easier.
Yeah, how long did you take?
Like 2 hours.
Yeah, that's too long. You should not do that.
I checked my work a lot.
Oh, okay. Yeah, that doesn't count. I mean, so how long did you take to finish
Probably
it?
just to rip through the problems of somewhere between an hour and an hour and a half.
Yeah, that makes sense. Yeah. So what about the rest? Who think it's not extremely easy? So then you need to be worried, I guess, a little bit.
Yeah, I guess extremely easy, no. But I think most of my time is just spent flipping through my notes, trying to find.
Yeah, maybe. Yeah, I think one way to learn this kind of stuff is that after every class, when you review lecture notes, then you close your eyes and try to think what you have learned. Okay, and try to interpret everything intuitively, right? If you think there's no intuition, it's purely math, so it means there's something wrong. Okay, so information theory normally is, at least for our class, is very, very intuitive, right? Something can be counterintuitive, but if you think in the right way, it's still intuitive. Okay, so yeah, so my point is that so if you can understand things intuitively, then it means that you understand. Okay, great. So yeah, let's continue our class. So in the last lecture, we finished talking about the optimization theorem, and we give the Z channel example, right? Hopefully still remember it. And then we talk about the joint typical sequences. Okay, so basically what do we mean if, let's say, we have two random variables, they are jointly typical. Okay, what does that mean? Right. Okay, and so here is the optimization problem for our mutual information or for our channel capacity, right? The goal of this guy is that we want to use it to maximize the mutual information, right? In your exam, you have one such kind of problem, but that problem is kind of straightforward, right? You don't need to use that. Who used that to solve it? Nobody. Yeah, that's good, right? We don't need that because it kind of, yeah, I want you to use intuition to solve the problem, right? But if you have no much intuition, then basically you have to use this approach. Okay, so basically this approach is a convex optimization problem, right? And if you solve the KKT condition, and then you'll see another list of conditions, right? So normally those conditions will not give you the solution analytically, normally, okay? But it will give you some idea of the structure of the solution. Okay, and then based on the structure, it may simplify your life a lot. Okay, so that's the purpose of it. And from the using the KKT condition, what we get is that so if we consider this quantity, right, the mutual information between y and a particular realization of x, okay, and if you see for the optimal distribution, so if this guy is bigger than 0, then so all this kind of mutual information are the same, right? And if this guy is equal to 0, then the mutual information can be less than the optimal value. Okay, this is basically the structure of the solution, right? So this will not going to be different among different letter x. Okay, it will be the same for all the x as long as their distribution PMF is bigger than 0. Okay, this is structure, right? Therefore, in practice, how can you use it? You may let everything to be equal and see whether there's a solution or not. If there is, then it's optimal. If there's not, then somebody have to be equal to 0. Okay, and then you can try, right? You can write a program to determine that. Okay, again, so this is not an analytical solution, but it will give you some idea on how to write the algorithm to find it. Right, so this normally happen for the convex optimization, right? And then and here we say, okay, so if this condition is satisfied, then we say it's a good ladder. Otherwise, when this equals 0, then it's a bad ladder. Right, so which is intuitive, right? So the optimal solution tells you that the probability of that is 0, then why do you want to use it, right? Then it's bad ladder. Okay, and then we'll give the example of the Z channel and try to use this condition to characterize the capacity of it and what is the optimal distribution. Okay, so and secondly, we talk about the joint typical sequence sequences, and so this is the definition of the joint typical set, right? So the key part here is that we have three conditions. We need to guarantee each one individually is typical, and then this self-information has also also need to satisfy this condition, okay? And the reason we need three conditions here is that so this single condition cannot imply this and that, okay? But if we use a stronger typical set definition, then one is enough, right? If you recall, the stronger basically means that so we define the difference between the empirical distribution of the real distribution is less than epsilon, right? Because for that one we work on each individual PMF, then we're fine, right? But this one we're working on the average, which is entropy, right? Then we're not okay. Okay, so yeah, this is a definition of joint typical set, and then we have a list of properties here, right? The first property is that so this guy, the probability of the entropy set is almost 1 as n goes to infinity, right? Which is of course true, right? And then so we can characterize the probability. Each of the probability is roughly about 2 power of n times entropy, okay? And so that's why it's called AEP, right? Asymptotic equipartition property, right? And the cardinality of the typical set is given by that, basically, right? We have upper bound and lower bound, right? When epsilon becomes small, then pretty much they're the same, right? Precisely, yeah, for this one, it's always hold, but for this one, we need to n becomes large, okay? The reason is because of here, right? So this guy has to be, this one goes to 1 when n is large, right? Otherwise, it's not, okay? So yeah, so when you review that and see each of the property here, and then think about intuitively why it is true, and whether you can prove it or not without looking at your notes. Okay, if you can do that, it means that you understand this. Okay, it's not that easy. So it's you need lots of practice. Okay, and lastly, so we have a very interesting property here. So basically, this means that if we have x tilde and y tilde, they are independent, but the marginal distribution is the same as px and py. Okay, so in that case, if we draw a random sequence of that, so will that be typical? Will that be in the typical set? Okay, intuitively no, right? Because they are not jointly distributed, right? So this typical set, is defined based on the joint distribution, right? If they're independent, how come they can be in a typical set, right? But the reason is that, if we have enough, number of this is large enough, right, then some of those will fall in the typical set, okay? And the probability of those guys falls in the typical set is characterized by the mutual information, okay? So this is the most important part. Okay, and then we'll have upper bound on this, and we'll have lower bound on that. Roughly speaking, this guy will equal to 2 power of minus n times the mutual information. Okay, so that's a very key part here. Okay, and then so so we'll start today's lecture. Yeah, so we're almost done with chapter 7. EEL6532. Today is our lecture 28. So we should have 39 lectures in total today. So yeah, we have only one topic, which is to prove of channel coding theorem. Okay, it's a real proof. Okay, so yeah, this is probably if not the only or the most important theorem here, or one of the most important theory in our class, right? So this will tell you how can we prove the converse and achievability in right way, right? We did that before, but it's too simple. It's hard to see the structure of the proof. Although we summarize a little bit, right? But still, it's too simple. But this one is not. So this one we can see all the important ingredient of the proof, right? And for all other proof, you'll see it's very similar to what we'll talk about today. Okay. And normally in the paper, many steps will be skipped. Okay. So if you read the information theory paper, you may see, okay, so some of steps is not easy to understand, right? Why from here to here is true, it's because they skip lots of steps, right? So all the steps are here. Okay. So yeah, just try to remember it, then you understand the papers. All right. so let's get started. Okay, proof. Okay, so, and let's recall what's the channel capacity. So the channel capacity theorem for DMC. Okay, so this is C equals to the maximization over Px of mutual information. Okay, so this is basically the theorem, right? So in order to prove it, so we need to do like two things, right? One is the achievability, or the direct part, and the other one is the impossibility, which is the converse part. Okay, so we'll first do the achievability with the direct part. Okay, so the thing we need to prove is the follows. We need to prove that for any rate less than the capacity C, there exists a sequence of Rn codes with vanishing probability of error. Okay, so this should not be unfamiliar, right? So this is what we did for the source coding theorem, right? So we show, okay, there exists a code, right? And then a sequence of a code, right? Then when this n goes to infinity, then the error will be equals to zero, going to zero, right? So this is basically the idea. Okay, so now the difficult part is, normally for the achievability, what we need to do is what? Construct a coding scheme, right? Like what we did before. So we indeed construct a coding scheme, right? Use the typicality coding, right? Then for the source coding, right? And then we prove that, right? But here, let's see. So normally constructing a scheme is the ideal way to do it, right? So if we can construct a scheme to show this is achievable, then, of course it's ideal, right? But it is very, very difficult, right? So it's years after this, people show there's kind of a coding scheme that can, constructive coding scheme, we can achieve this capacity, okay? So one of the examples is called polar codes. So that was developed very near now. So it's like maybe a bit more than 10 years ago, okay? And now we use that in the 5G, 4G, 5G system, okay? But it's way later than the theorem, okay? Then, what Shannon did here, which is one of the most important idea in this class, is that, okay, so is there a way that we can prove this without constructing it, right? So without an explicit construction of a code, is that possible that we can show this is indeed achievable, right? What it means is that if we do not construct a code, there's only one thing we can do, which is we show there existed, but we don't know how to construct it. That makes sense somehow. That what is exist, how can we show something exists, right? So the idea is called random coding. Okay, so basically, so this is a brilliant idea. So basically what it does is that, okay, so now we randomly generate a class of codes, okay? And then we show, okay, so at least one of those can achieve this capacity. So that's basically the idea, right? So we can show the existence without the construction of it. Does that make sense? Right, so let's see how we do that, right? So it may not make lots of sense to you now, but it will, I promise. Okay, so let's write down the idea here. So the idea is that instead, instead of building a specific family of codes. Okay, so this normally is very difficult, right? Because people build that years after the theorem, so it's very hard. Okay, so instead of doing that, we average over a random ensemble of codes. Okay, so let me describe again what is the idea, right? First of all, we generate a distribution, okay, and then we generate a code randomly, right? So basically what we do is that the key here is what? Is to compute when the error probability will go to 0. Okay, so of course, we need to define, if we can find a code, right? We don't know how to construct code, but we know the code might exist, right? So when you design a decoding scheme, right? Let's say if the code exists, right? It's a random variable, okay? And then let's say if we can decode it, then what is the error probability, right? So everything will depend on the error probability, right? So what is the condition the error probability will go to 0? Remember, the error probability here we care about is what? Is the maximum error probability, right? It's not the average, it's not expectation, it's a maximum, right? But by some random coding argument, so what is easy to compute is the expected average error probability. Okay, we're gonna show this will go to 0 first, and then we're gonna convert this to the maximum error probability. Okay, so that's basically the idea, right? So if you say, okay, so we randomly generate the code, okay, and then we compute the expectation of error, and that goes to 0 under some condition. So this condition, you'll see basically it is this condition. R has to be less than C. Okay, that will be the condition. Okay, and then then from here we show, okay, the maximum error probability will also go to 0, and then we're done. So that's basically the idea, right? Without constructing the code. Yes?
So what if the average error probability goes to 0? That means the max goes to 0.
Yeah, there's a non-trivial proof on that. Yeah, so, this is a good point. I don't mean that for the same code, the average error goes to 0, it implies the maximum error goes to 0. No, we need to change the code, right? But there's a non-trivial step we're gonna go over. Okay, yeah, let's see whether we can get this random coding idea. Okay, so the generate of the ensemble of the code is very easy, right? Because we have a distribution on X, on the code word, Px, right? So we just randomly generate all the symbols based on Px, okay? So the first step is that we're going to fix Px first and generate how many symbols? Capital M, right? Capital M is the size of the cardinality of our source symbol, okay? And the capital M will equals 2 power nr, right? R is the rate of the code. Okay, rate basically means you can understand per unit time how many bits we can transmit. Okay, so we're going to generate this codebook. Okay, we denote the codebook as a C, right? Or explicitly it's a Cn because it's a function of n. Okay, generate this at random with, this is important, with IID entries based on Px. Okay, so this is another non-intuitive but very interesting idea, right? You can think this is the most basic or the simplest thing we can do, right? How to generate the codebook? Just randomly generate it with IID, right? There's no correlation, right? If there's a correlation, we need to design a correlation, right? So which is, we have no idea, but we just use IID here, okay? Okay, so let's see. Now we can think the codebook as this. So this is the code word. Okay, the length of that is n, right? And we can think, let's say, if here's the message index, so this is the first message, right? And then, so this is another line here, another row. So this is the second message, right? So we denote that is as x1, and this is x2. So each of them is a code word. Okay, for the first symbol 1, we just transmit that over the channel. For symbol 2, we transmit that over the channel, right? And then here, the total number of code word here is 2 power nr, right? So therefore, the index here is 2 power nr, right? The last one is x 2 power nr. Okay, very good. So this is a code book generation, right? We just generate the code book this way, and each element is IID. Is that clear? Is that clear? But think a little bit, right? So if we so if we consider each of the element here is a random variable, so they are IID, right? But if we generate them, right? So it's finite number here, right? If we compute the empirical distribution, they may not be IID. Does that make any sense? Right, so there's a catch here. Okay, so you may think, okay, so I mean, if you look at this at your first glance, it may not make lots of sense, right? Because for the code there should be a structure. IID means there's no structure. Right? Yeah, when I first see that, it doesn't make any sense to me, right? IID, why? I mean, in practice, for example, if we use repetition coding, right, there's a structure there. We transmit 0 3 times, transmit 1 3 times, right? Not like randomly, right? But the catch here is that, so this is a weird, it is a genius idea, right? The distribution is IID, but if you have this already, you have a code book already, when you compute the empirical distribution, it's not IID anymore, because we have finite number here. That makes sense? Just try it, right? For example, let's say we have let's say we want to generate like the length 3 code book, right? Let's say if we randomly generate it, you can have 1 1 1 0 0 0. That's it. You can have 1 0 1, 0 0 1, right? But if you have those realization, and if you can compute the marginal distribution and joint distribution, they are not IID. There's a structure there embedded, right? Yeah. Okay, and yeah, you may think a little bit, right? Yeah, maybe afterwards it'll become more clear. Okay, so this is a code book generation. This is the first step, right? The second step here is that, so we're going to tell the code book to the transmitter and the receiver before transmission. It basically means that all the transmitter and the receiver know the code book exactly. That makes sense, right? Yeah, otherwise, how can I do the decoding, right? So basically, we say the code book. Yeah, what I'm saying here, they are all generic. So it happens to all the information theoretical achievability proof. Okay. For all other theorem, you'll see this kind of thing. Okay, so the code book is revealed to transmitter and receiver before before communication takes place. Communication takes place. Okay? Yeah. This is the second step. Okay, so now we're ready to transmit, right? And then when you do a encoding, right? What is the encoding? It's a mapping from the message to the code word, which is exactly this. Okay? So we encode 1 as this code word, encode 2 as this code word, and so on. Right? So this is encoding. So x of m is the m's row of the generated code book. Okay, so m is in the set of m, right? And the set of m is from 1 to blah, 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 to 2 power nr. Okay, so here you may not realize it, but there's a small thing here going on. So we call this random coding. The random coming from the codebook generation. Okay, but when we assign the index here, it's not random, right? So we just map this 1 to 1. You can do random, but we don't need to. Okay, but later on, for some other proof, we may need to do a random assignment here in order to make our life easier. But here we do not need. So yeah, the random coding coming from the codebook generation, not from the code word assignment. Okay. Okay, so this is the encoding, right? And then we pass the code via the channel, via the DMC channel. Okay, and then at the receiver side, we're going to do a decoding. Okay, so now let's see how we can do the decoding. Right, so for the decoding, so we mentioned that in our last class, we're going to do a joint typical decoding. Joint typicality decoding. So basically for the decoding, our goal is that we observe y and then want to recover small m to see which one is transmitted, right? Or based on y in practice, we're going to estimate x, right? And then because x and m is 1-to-1 mapping, then we know m, right? And in order to do that, right, from signal processing class, for example, or from a statistics class, what can you do here, right? Basically, if you observe something, right, then you want to estimate, for example, the noise-free version of it, right? Then what do you do? What algorithm you have learned to do that? Yeah, we cover a few of them in our communication class, communication theory class. Remember it? Yeah, I'm pretty sure you learned that from other classes as well, like digital signal processing. Yeah, let me remind you a little bit, right? So did you learn anything related to Bayesian, rule, Bayesian statistics? So there's one approach called maximum likelihood, right? There's another one called maximum a posteriori. That's it, right? MAP, map, right? You learned that, right? So here we can do the same thing, right? We can do maximum likelihood, we can do map, we can do even MMSE, minimum mean square error detection, whatever, estimation, right? Did you learn that as well? No? Yeah, you learned. Okay. There, from statistics or from statistical signal processing, so there are like estimation theory, detection theory. We have many tools there to use. Okay, we can use either of them here. Okay, but we don't. The reason is that this is easy to analyze the error probability. Okay, but in practice, you can definitely use whatever you want. Is that clear? Okay, so what I want to tell you is that, okay, so this is not like a magical, right? There's many things we can use here, right? There's a reason that we want to use the joint typicality decoding, right? Because it's easier for our proof. Okay, our goal is to characterize error probability, right? So in practice, after Shannon's paper, there are so many researchers, trying to characterize what is the error probability for some code. Not this random code, right? For some well-constructed code, what's the error probability for those code using ML decoding, right? So actually, currently what the decoding approach or the estimation detection approach used in current 5G or Wi-Fi system are this. They are using kind of MAP and ML. Okay. They don't use typicality. Okay, it's not practical, just for the proof purpose. Okay, so let's see what that is. So basically here we let y denote the received signal or received symbols. The received and observed channel output. Okay, and then is our decoding, right? So what we used before is G. So this is our decoding function, right? So basically what we'll do like this, right? So we claim we receive M hat. So that's the index of the message, right? And of course that will be one of the elements in the M, right? So when we claim M hat under one condition, the condition is that if if this is the unique index such that the received symbol X M hat and Y, which is the received signal, they are jointly typical. Okay, so basic procedure is that, okay, we receive a Y, okay, and we know our typical set, right? And then we're looking for all the X, right? And if there exists only one X that is joint typical with Y, then this X is our transmitted X, right? And from this X, we know what is M. That's how we decode it. Now you may wondering, okay, so what if there's no X to be joint typical with Y, right? This is one thing that can be an error, right? And another case is that, okay, what if there's one more indices or one more X, more than one X, that is jointly typical with Y, right? Then for both of this event, we declare an error, okay? We have to only find one X to be joint typical with Y. Is that clear? Okay. It sounds a very harsh condition, but then we're going to see that it happens all the time. Then we declare error. Okay. Otherwise we declare an error. Okay, great. Yeah. So this is what we do. This is a random coding argument. Okay, and you can see that we have an algorithm, but we're not really constructing a code. We just randomly generate a code. Okay, and now you may wondering, okay, so we just randomly generate a code, whether it's good or not, right? We don't know, right? So what we do here is trying to, as we said before, trying to characterize the expected average error probability. Okay, so that's easy to compute. So our goal here is to analyze the expected averaged or expected averaged, or we just call it the average error probability, right? We don't call it probability of error. Okay, so here you can see that we have two important adjectives here, right? So one is expected, the other one is averaged, right? So they are different, right? So what is expected? So that's take the expectation, right? Take the expectation over what? Over some random distribution, right? So what is the randomness here? Not average, expected.
Well, expectation of the
Average. Yeah. So expectation is over what? Yeah, we first need to understand what are the randomness here, right? So in our system, we have two sources of randomness. One is the code generation. The other one is the channel. Okay, so this expectation will take over what? The code book. Okay, so this is important. So this is over all code book, right? Meaning that, so we're going to take average on all the possible C here, or Cn here. Okay, you'll see that will make our life way easier. Otherwise, there's no way to analyze. Okay, and this guy is just, this is easy, right? So this is the average error probability. So that's the average over all the messages. Okay, so this is what we're going to characterize. Any questions so far? Okay. Now let's try to compute it. So now this is the expectation of the probability of error. So we use the PE bar to denote the error probability. Okay, of a code book C. Okay, and the expectation is over all the code book. So this is something that we want to compute, right? Okay, so let's write it down. So what do we mean by this, right? Then we'll have summation over all the possible code book, right? And then, so what is the probability of a code book? Multiply the probability of error. So we denote this by this. I should have an end here. Okay. Yeah, so this is basically is the expected error probability, right? And then we can further write it more explicitly. So this, and then we write this guy out, right? So average means 1 over 2 power nr. And then we sum over n from 1 to 2 power nr. And then the error for each message, right? M, and given the code book. Okay? Right, then what we're going to do is that, so normally when we have this two summation, okay, we try to switch the order and see if we can have anything interesting. Okay, so now let's switch the order here. So we have this. Okay, and then we have the sum over all the code book, PRC and PEMC. Okay, very good. And then what do we do? Right, so now let's look at this term. What does that mean exactly? Right, this is for message M, right? And so for each message M, then we can have some error, right? And we average it over all the possible code book. Right, yeah, let's see the code book generation here. Let's see what you can find, right? So basically, the code book is generated in an IID fashion, right? So for example, so this row will happen with some probability. It could be here. It could be here as well. Or it could be here. It could be anywhere, right? So basically, it means that if we average the error probability over all the code book, it means that the identity of M doesn't matter anymore, right? Would there be a difference if M is 1 or M is 2? Right? Would that matter? It will not. The reason is what I just said, right? So because we're all averaged over all the code book. Okay, all the realizations of the code book, right? So this, the same code word can be assigned to 1, can be assigned to 2, can be assigned to whatever, right? Therefore, the identity of M doesn't matter anymore, right? So, okay, not black. So basically, what we can say here is that, so for simplicity, since the identity of M doesn't matter anymore, so what we can write here is PE1C, right? Just let M equals to 1, right? Because it doesn't matter, right? Is that clear? Right? Okay. Then why we want to do this? The beauty of that, because identity M doesn't matter, so this part is gone. Right? Because we have from 1 to 2 power NR and normalized by 2 power NR, right? This is gone. So we don't have that anymore. So what we have is only this guy. Okay. So what does that mean? How can we interpret it? Right? And remember, codebook are randomly generated. So now this is expectation of this error probability. Right? So can you interpret it in another way? So because now we're transmitting the first message, right? So that's fixed, right? So this basically means that what is the probability that we make a mistake when the first message is transmitted? Where the random variable is, where the randomness coming from the codebook generation. Does that make sense? Of course, we need to consider channel randomness there, right? But we don't need to really care about it.
Is it like the probability that there's more than one copy of that message in the codebook?
Almost. And the other, you're one step ahead of me. So, and we have another probability that is, what if there's no one in our joint typical with Y? Exactly, that's right. But we're going to write it a small step here. So this is a probability that the decoding of Yn that is not equals to 1 given small m is 1. Or we can write capital M is 1 because now we consider random variable. Okay, so important here is that, so now for the random variable Y, the decoding of that is not equal to 1. The probability of this means this guy. Does that make sense? Right? So because it's an expectation over all the codebook generation. Okay. Okay, so now next step is to compute it. Okay, so when you compute it, we have to follow your idea here, right? Because in order to compute an event, right? This is an event, right? So basically we let E, so which is an error event, equals to this guy, not equals to 1. Okay? We let this denote the conditional error event, right? So here, we didn't write it, but it means that when 1 is transmitted, okay? Okay, great. So this is the error event, right? And then we'll want to compute what is the probability of this error, this event, right? Okay, how can we do that? Okay, so this is a one event, right? Normally, when we want to compute the probability of an event, we want to decompose it into a number of events which are easier to compute, right? Okay, so as we said before, so this will equals to the following. We say it's the E1C. So E1C is basically the event that, so this guy, when the first message is transmitted, and Yn, right, because it's random variable, right, Yn, so that is not in the typical set. Okay, so this is the first event, right? So, and then, or, remember here is or condition, right? So it means that if one of those happened, then we are in error, okay? Or we say it's E2 or E3 or E2 power NR, and clearly, so this guy EI means the fact that this guy and yn, so here not equal, not in, right? This is in this, okay, for all I bigger than or equal to 2, right? So this means that the right one is not in the typical set, but the wrong one is in the typical set. Does that make any sense? Yeah, just look at this. Try to absorb it.
Can you say that last part again?
Yeah, last part is that, so last part is this one, EI. This means something wrong is in the typical set, right? So what we want is this guy in the typical set, right? And there's only one of this guy in the typical set, then we're okay, right? But now, the first event basically means that, so the right one is not in the typical set, but there's a wrong one, meaning I is not one in the typical set, right? Yeah, because if this guy is in the typical set, we're going to declare this one as the transmitted message. Then we have an error, right? Is that clear? Yeah, this is very important. So now, next step is to compute PE, right? So then, so how can we compute PE, right? Yeah, let's say PE given M is 1, right? And this guy is equal to this guy. Right? So now we can decompose E by all of this event. But the relation between them is OR. Right? OR basically means that they can happen in the same time. Right? So can we just write, for example, maybe, yeah, let's write one more step here. So this equals to E1C or E2 or E3 or until E2NR given M equals to 1, right? So can we break them, right? So can we say, okay, if we want to, because, computing each individual one might be easier, right? So what if we compute this guy, given M is 1, and then we just compute the rest of those. Okay, so we basically write in each individual probability here, right? Can we do that? So are they equal? No, right? Because this and that can happen at the same time, right? They're not equal, but what's the relation between those two? So because for the error probability, what we need is what? Upper bound. We don't need to compute it precisely, right? If the upper bound goes to 0, then it will go to 0. So we just need an upper bound. Is that an upper bound? Is that true? This inequality? Yes, it's true, right? What's it called? So basically that is something like this. Probability of A or B will be less than or equal to probability A plus probability of B. Right, what is that? Union bound. Okay, so by union bound we can get that. Okay, so in next class we're going to compute each of those. Okay, and we have to continue, right? So we can now finish it within 15 minutes. Okay, thank you.